Hi, everyone. Thank you so much for joining us today. Welcome to the Speeding Edge, NASA and Supersonics. The 30,000 foot view, or in our case, about 60,000 feet, big picture focus of this panel is to highlight the exciting advancements in supersonic capabilities and discuss steps to enable a world of high-speed flight. For our audience, if you want to submit questions, you can do so via the conferences.io link, and I will keep an eye out for those. And with that, let me introduce our panelists. So we have Michael Bunano.
Hi.
Go ahead.
All right. Well, good morning, everyone. I'm very excited to be here to talk to this group. That was an exciting video we just saw. I'm a air vehicle IPT lead for the X-59 project at Lockheed Martin Skunk Works in Palmdale, California. I've been working on commercial supersonics for a big part of my 20-year career out in California. And it's very exciting as we just held our rollout, which you saw footage from, and we're getting ready for first flight later this year. Supersonics has been something that I've been passionate about. I've always loved going fast, and really excited for the opportunity that this project has for our industry and for our country to allow people to hopefully eventually get where they want to go about twice as fast as they can today. I think we've got a video, an additional video that can give you some additional context on what X-59 is and how it can be beneficial to our country and to the general flying public.
NASA is taking a huge leap to address challenges associated with supersonic air travel. One of those is reducing the disruptive sound to people on the ground caused by supersonic flight. NASA's Quest mission is the culmination of decades of research and is centered around a new aircraft called the X-59. NASA has contracted with Lockheed Martin Skunk Works to build a new full-scale X-plane to help solve one of the most persistent challenges, the sonic boom. Since 1973, the FAA has banned commercial transportation from flying at supersonic speeds. The ban was in response to the thunderous sound of a sonic boom, caused by shock waves created when an object travels through the air faster than the speed of sound. The Quest mission has two goals. First, design and build a unique shape that will reduce the loudness of a sonic boom reaching the ground to that of the sound of a closing car door. And second, once built and tested, fly over a number of U.S. communities to gather data on human responses to the sound generated during supersonic flight to find out if the noise is acceptable to the public. Then, hand over the data from communities to federal and international regulators to help establish a noise standard for overland supersonic flight. Researchers understand that there is still a need for the development of full-scale piloted X-planes to help close gaps in our understanding of aeronautic principles. The team will soon kick off a series of X-59 flight tests that could assist in opening new markets for faster air travel over land.
So thank you for that. And now we will go to Jim.
Good morning, everybody. My name is Jim Less. My friends call me Clue. That's been my call sign since my Air Force days. I've been working with NASA now, flying for NASA for over 13 years. And most of that time, we've been doing a lot of fundamental research on sonic booms, leading up to the idea of building a quiet supersonic airplane like the X-59. And I grew up, like Mike said, I grew up reading everything I could about X-planes and flying supersonic, and never imagined that someday I'd get to fly a supersonic X-plane myself.
Okay. And I think you win the award for most ironic call sign. I'm pretty sure they don't let any old clueless person fly these kinds of aircraft. So we've heard from the manufacturer side of the house and test pilots for supersonic research aircraft. Let's go to the industry side with Troy Follick.
Thank you. Troy Follick. Good morning to folks and good afternoon to other folks. come to you from Boom Supersonics. We're a startup. Our mission is to bring commercial supersonic flight back to the commercial airways. Like the first or the last video showed, we won't plan to fly our aircraft called the Overture over land, but over water we can fly supersonic and not violate any of the FAA or international laws. So a little bit about me. I've been in the industry 30 years. Excuse me. Like Mike and Clue, I've wanted to fly since I was a little kid. Didn't make the military route for physical reasons, but I got my private pilot's license and then really wanted to use my engineering degree to bring commercial flight faster and faster. So in my history, I've worked on an airplane that I would still consider the fastest subsonic airplane, which was a Gulfstream G650, which has a cruise speed of Mach 0.90, which is pretty fast in straight level flight. There are other companies who claim to fly faster in a dive, and that's super exciting too. But I like the straight and level flight. A little bit about us. So we have created a supersonic demonstrator called XB1. It's out in the Mojave Desert now, and we're going through some ground testing as we speak, and hopefully to take it to the skies in the next couple of months. And with that, I think we have a video to share with the folks online. And with
Great.
that, I'll turn it back to you, Michelle.
Thank you. And yes, I'm from the FAA. My background is in aerospace engineering and engineering project management, but today I will be your moderator. So one of the things we heard already was what a Mach number is. We have a pretty broad audience, so let's say Jim, Clue, you briefly explain what a Mach number means, as well as what it means to go supersonic, if we want to toss it up to Michael.
Sure. The Mach number is just a way of measuring your speed relative to the speed of sound. The speed of sound is about 750 miles an hour at sea level. It decreases slightly as you get up in altitude, but it stays roughly about that speed. So Mach 1 is just at the speed of sound. Above Mach 1, you're now going supersonic, and that's where you're producing these shock waves that come off the aircraft that produce the sonic boom that we are trying to quiet with the X-59.
Thank you. So now that we have a basic understanding of that, let's talk performance characteristics for each aircraft. I think let's go to Jim, you first on the X-59. What speed are we're talking about for this, and altitude as well for operations?
Okay, so for the X-59, we have a design condition that is supposed to be its quietest, and that is going to be about Mach 1.45, so 1.45 times the speed of sound, and we'll be doing that around 55,000 feet.
Okay. And how about you, Boom, Troy?
Yeah, so our demonstrator XB1 is designed for a Mach 1.3 at about 40,000 feet.
Okay, 40,000. And for your commercial aircraft, when you plan to deploy, is that going to be the same, or are you thinking something different?
So for Overture, and I apologize for not talking about both, but for Overture, it's a Mach 1.7 up to 60,000 feet. Originally, we looked at maybe doing the Concorde speed of Mach 2.2. However, we really want to get some area ruling throughout the fuselage and some very unique curvature in the wing to help with low speed performance, because we won't have afterburners on the Overture. So with those couple of things, we've reduced the speed to Mach 1.7. Composite materials that are in use today by the other aircraft manufacturers like Northrop Grumman, Boeing, Airbus, Lockheed, we can use those material systems with little additional testing for thermal.
Michael, for the X-59, Troy just talked about the curvature of the wing and how the design is meant to change the performance. How are we on the X-59 dampening shock waves and noise?
Yeah, the low sonic boom characteristics of X-59 really are all dependent on its shape. Every single aspect of X-59, from the tip of the air data probe in the front of the airplane through the nozzle at the end of the airplane, all of those features need to be carefully designed and choreographed so that they work together to dampen that sonic boom. That's a long, painstaking design process in order to iterate on those features and look at different combinations and different arrangements. That's all done now. We've validated that design in a supersonic wind tunnel that NASA provided and ran the test for. The results from that test look very favorable in terms of agreement with our CFD, computational fluid dynamic analysis, that we use to actually design the airplane. And so we're very confident that when we progress to flight later this year, and then ultimately into subsequent phases where NASA takes over primary responsibility, that the airplane is going to do what we designed it to do. And that is to make a sonic boom that's dramatically quieter than any other airplane that's ever flown supersonic before. Traditional supersonic airplanes, something like Concorde, had a sonic boom of more than 105 decibels in the scale that we use for sonic boom analysis. And X-59 is designed to be about 35 to 40 decibels quieter than that, where it's like that proverbial car door we heard about earlier.
Okay, I think you just answered someone's question. So that's good, thank you. About a car door sound compared to previous sonic booms. All right, so let's talk about the flight test a little bit. Clue, can you please share your experience with us about being a test pilot and what we're trying to achieve with X-59 flights?
Sure. Since I've flown with NASA, I've spent more time supersonic with NASA than I ever did in the Air Force. We've been mostly creating sonic booms and trying to understand how the atmospheric conditions of the day affect that sonic boom as it travels to the ground, along with the impact of different types of buildings and structures on the ground and how that affects really how much it startles people or annoys people. But all that is just preliminary data leading up to designing an aircraft that can minimize that sonic boom. I think Mike probably could tell us a little bit about the first phase of flight test for the X-59, where we prove out that aircraft and make sure it's ready to go.
Absolutely. So X-59, at this point, we've had our rollout event and the airplane is physically built. We're conducting the final ground tests and verifying that all of our systems work together as designed and as intended. Also preparing for our first engine run, which is upcoming shortly. So once all those tests are done to verify that the systems are safe, we'll be getting into an envelope expansion campaign, which basically means we take an incremental approach towards showing that the airplane is safe. First, at slow speeds, just basically take off and land safely and have adequate handling qualities. And then we have a very measured and rigorous buildup process where we'll progressively get faster and higher. And by the end of that phase one test campaign that Jim asked about, we'll have shown that the airplane does everything we said it was going to do and that NASA required of the airplane, and that it's safe to fly. And that's really when the exciting part of the program happens, in my opinion. Phase 2 and phase 3 that NASA will lead up, and that's the mission that we've designed the airplane for, to go out into the communities and really help hopefully repeal this ban that was put in place in 1973.
Okay. So can you elaborate a little bit on that? What is the purpose of the output of these tests? Can you clarify that again? You're taking this research and giving it to.
Oh, sure. I'll take that and include that. Maybe you can jump on too.
Sure.
So the fundamental mission of X-59 is it's a flying signal generator. When Congress put the ban in place back in 1973, we didn't yet have the technology to design airplanes for mitigated sonic booms. It was kind of an all or nothing thing. And in just my personal opinion, I'm glad that Congress put that ban in place because sonic booms are very loud. I don't know how many audience members have heard them, but if we were hearing Concorde level sonic booms over our heads every day, all day, none of us would be very pleased with that. So I think that the regulators did absolutely the right thing when they put that ban in place. Technology now, though, is 50 years advanced compared to when that happened. And thankfully, we've been able to leverage that technology and we can design these airplanes such that rather than that very loud double bang, the noise is much quieter. That said, the ban is still in place. So as of right now, even if you were to build a very quiet, nearly inaudible supersonic airplane, the rules are such that that would not yet matter. And you would still not be prohibited to fly at supersonic over land. So what we'll do with X-59 is we'll go out and prove that the noise from this type of airplane with this type of design is dramatically quieter. And NASA will fly it around different parts of the country. And it basically help support development of a database. And I think, Jim, you can elaborate more on how NASA intends on flying phase 2 and especially phase 3.
Sure, Mike. So Mike talked about phase 1, which is proving the airplane safe to fly. And as he said, then it gets exciting after that. What we're calling phase 2, we're going to be flying it locally here at Edwards Air Force Base, where NASA Armstrong's Research Center is located. But we will be going out and our scientists will be measuring every aspect of this aircraft and really the shock patterns and the sonic booms as they reach the ground. We're calling them sonic thumps, actually, because we really don't think it's going to be a boom. We're going to use a wide array of techniques to measure these shock waves. We're going to fly other aircraft. We've got an F-15, specially modified F-15. We're going to fly right up close to the X-59, up at altitude, and actually measure the shock waves as they come off the aircraft. We'll then use a camera system to actually take pictures of the shock waves as they travel off the aircraft and extend down to several thousand feet below. And then finally, down at the ground, we're going to have an array of microphones measuring the sonic thump as it comes over and prove that we're really getting that 75 dB that Mike was talking about earlier. And then after that, as he said, phase 3, we take it out into the communities, several locations around the country. We haven't picked those yet, but we're working hard to figure out the right places to go. And we're going to use basically audience participation. We'll have volunteers throughout the community deploying mobile phone apps and flying over their houses during the day. I mean, we're up high at altitude. You're not going to see or hear the actual airplane. And we're going to find out, can you hear the sonic thump? Does it disrupt your day? Does it startle you? Or as we expect, I think a lot of cases, people aren't even going to hear the sonic thump unless they're expecting it and they're knowing to listen for it.
Yeah. So does Boom Supersonic want to change their name to Thump Supersonic now? I'm just kidding, Troy.
Great question. Great comment.
But can you elaborate on your business case for us? Because it's a little bit different than the test aircraft, obviously. I know you have a test aircraft of your own, but you do plan on operating commercial passenger transport, right?
Great questions, Michelle, and I appreciated the comment. So listening to Mike and Clue, I want them to be super successful, NASA and Lockheed, in the X-59, because that data that they get will hopefully be shared with industry, and then we can create a second aircraft. Obviously, our first is called Overture, that aircraft, and it will boom. We won't call it thump, but it will boom, but it'll only do it over unpopulated waters. And so that's Atlantic, let's say Boston to London Heathrow, or even into Paris, and then from the West Coast, Seattle to Narita, Japan. I saw there was a question about runways and Concorde. So for us, we're designing our first airplane to operate between a 10,000 foot and 11,000 foot runway. Obviously, the shorter distance you go, you can remove fuel to get into shorter runways, but that also reduces your range. So you have to think about those two things in conjunction. But yeah, our business case, like the video said, there's 600 plus routes today that Overture could service and save you half the time, basically flying twice the speed of today's subsonic planes. And if we did have to fly overland, because there is a use case of some major cities in the United States, coast to coast, we can fly at Mach 0.94 overland. And as long as, there's not a gust, and that's why we picked Mach 0.94 at altitude, we won't create a sonic boom. There was some news a few years back, maybe 4 or 5 years ago. A company up in Canada that produces aircraft flew one of their test airplanes and broke the sound barrier, which was pretty cool how they did that. But that's not the intent of their airplane, but it was cool that they did it, and it's exciting. So I appreciate the questions. Keep them up, and I'm looking forward to all the output and all the fun that they're going to have at NASA and Lockheed Martin with the X-59.
So if the upcoming supersonic flights are successful, this is a question from the chat, how long will it take to design and fly with people? So that's probably more of a question for Troy, since you're doing the commercial development.
Okay, thanks, Michelle. Well, I thought Mike did a great job talking about computational fluid dynamics. So we're doing a lot of CFD work on the aircraft Overture that will be the civilian commercial flight aircraft. Right now, we're estimating a program of around 10 years. So hopefully, late this decade, early next decade, we'll have that airplane out in service. And I say that I don't want to put pressure on my friends at the FAA. That's why I'm not giving a specific date, because you want to work well with the regulators, whether we're working with an aircraft certification office with the FAA or the engine certification office at the FAA. We want to have a great relationship. So that's why there's a window, just to help people understand.
Yeah, thank you. Do either of you want to add on what you think, or what have you heard?
I think the development timelines that Troy advertised are very realistic. I would say that right now, because it is illegal to fly supersonic over land, the clock hasn't started ticking on the development, not of Overture, but of a product that would be capable of flying supersonic over land. So first things first, we need to be, at least as it relates to a supersonic airplane that's capable of overland supersonic flight, we need to perform with X-59, get it into the airplane or into the air safely and flying its mission so that we can collect that data that I alluded to earlier. I think only then would many leaders have confidence to truly embark on the full-scale development effort to build a large commercial supersonic overland airplane. So that type of product is more than 10 years out, in my opinion, because the rules haven't changed yet.
Yeah, I guess I didn't finish the whole story when I was talking earlier about phase 3. After we gather all this data, NASA intends to provide this to the regulators. And as we like to say, we want to change that speed limit to a sound limit, and then get rid of the restriction on supersonic flight, and then just restrict airplanes that have a sonic boom louder than a certain level. And we hope to find out, is that 75 dB, or is it higher or lower than that? And so that's a large part of what we're going to do with the X-59. And then as far as transitioning the technology, one of the other outcomes or products from this whole X-59 program is all the knowledge that we've learned about making quiet supersonic airplanes. And we will share that. It's essentially in the form of CFD code, like Mike and Troy were talking about, that would then be available to industry to use to design an airplane. They don't have to start from scratch. They can use what we've learned to predict, is their design going to be quiet enough when it gets airborne.
Okay, Thank you. Speaking of development, what is a challenge, success, or surprise that you guys have encountered in the development process? Is there anything that people would be surprised to know? We'll go to Clue you first, I guess, since you were just talking.
Okay, one of the unusual aspects of the X59, if you look at a picture of it, if you remember it from the video, it has a very long, skinny nose, as Mike explained, designed to spread out those shock waves and produce the thump. But that gives the pilot no forward-facing window. So in addition to designing the airplane, we've had to build we call it an external vision system, which is a system of cameras and TV monitors that take the place of a window. We have a virtual window out the front. We're looking at a TV monitor that's basically aligned with the outside world, showing us where we're going. And that's a new concept. Hasn't really been done before.
Yeah, I'm glad Clue brought that up. I think that's been one of the exciting successes so far on the program. The external vision system that NASA developed has already been tested on surrogate airplanes like a King Air, I believe. And I think there's a lot of benefit from that technology, both for X59, but also the broader community. Potentially could be useful to Troy or Boom as they embark on their development efforts. And even subsonic airplanes, I believe, can benefit from that technology. Some of the challenges we've had are the complexity of these airplanes. There's just a lot of systems that go into making an airplane safe to fly, and all those systems need to communicate with each other and collaborate with each other. And sometimes it's a painstaking process to go through and just very rigorously make sure that everything works as it should. And that's probably not to be unexpected, but it is a challenge. So I wouldn't say it's a surprise, but it's hard work developing a first of its kind supersonic X-plane. And very thankful to have a great combined team between NASA and Lockheed Martin to work on this development program. That's been one of the big, not a surprise, but a tremendous thing I'm happy about on this program is how collaborative we have been between NASA and ourselves as the contractor designing and building the airplane. And that's really helped us progress to where we are.
Troy?
Oh, I mean, for us, when we saw the X-59's virtual window, as Clue called it, it's absolutely needed. Concorde had a movable nose, so when that visor, as it's called, moved down, it allowed the pilots to see forward looking because cameras weren't as small as they are today. So for XB1, we have created something similar to the X-59, added some extra windows to get your reference to the horizon as you're coming in at that higher attitude of the aircraft or angle of attack. And then for Overture, very similar, we will use an augmented forward visual system to augment our windows as well. We'll, like X-59, we'll have windows too, but the pilots will need that augmented view so they don't have to crab to the runway. And crabbing means flying at the side where the nose is pointed away from where you're actually landing. So yeah, we're excited about the technology advances, both what we have today and what's coming in the future. And we'll apply those to the Overture aircraft that we plan to bring into service later. Back to you, Michelle.
Thanks. Yeah, I'm glad both of you guys were able to show the aircraft. Troy, the Overture looks very fancy, at least how it's presented in the video, right? So how accessible to the public do you imagine these flights being? Like, would this humble panel moderator be able to afford it?
That's a great question, Michelle. So Concorde was, think of this in the $1970, about a $10,000 ticket to fly between Paris and New York or London and New York. That's an exorbitant amount of money. Today, we're targeting our first class and premium economy class seats with potentially anywhere between a 30 to 50% markup. So, today you could buy a ticket, for about $3,000 in one of those seats. So if you take that plus, times it times 1.5, that's about what you would pay for that ticket to reduce your time in half. I think that's a very valuable benefit to the consumer.
Yeah, thank you. It's good input. So something to keep in mind for saving for the future. No, I'm just kidding. So we talked about time frame for the operations to become available. What limitations do you guys foresee in the future to enable these flights? We can go to Michael. How about that?
What limitations? Well, I think there's a lot of advances that are still needed to enable supersonic overland flight. We've talked a lot about the work with X-59 and sonic boom, but there's others as well that thankfully NASA and other industry members like Boom are working on. One is the development of new propulsion systems that enable efficient, quiet flight. That's not needed independent of whether or not you want to fly supersonic overland, and that's a key enabler. Is the development of those new propulsion systems. You can't use the exact same engines that are used on subsonic airplanes today. They just won't integrate into a supersonic airplane effectively. And so that propulsion system development is very important. And then there's other regulatory work that is very important, working with the FAA to define what the rules are for future supersonic airplanes. There's certain aspects of the regulations that are that need updating, that were last changed in an effective way decades ago, and technology is different. And sometimes because there have been no supersonic airplanes introduced since Concorde, we need to continue working with regulatory agencies like the FAA and other international organizations to make sure that the pathway towards certification of a future commercial product is there. Those are some of the key things apart from the sonic boom work that I'm very, very involved in.
Jim, anything to add?
No, I think Mike covered that pretty well. And the first step we feel at NASA is to get the rules changed and show that supersonic aircraft can have a quiet thump. But then there's a lot of the practical issues that do need to be worked on. And as Troy was talking about, making it more affordable for the general public.
Okay, so we talked about changing design a little bit. That gets a little bit into sustainability. So what techniques or new technologies are you guys utilizing to keep sustainability in mind?
I'll take
Troy,
that.
you wanna? Yeah, thank you.
Yeah, Michelle, I'll take that. So for Overture, and it'll be using 4 engines. So using SAF, Sustainable Aviation Fuel, is critical. And there's 2 types of SAF. There's today's SAF, which has aromatics in it, and then the SAF of the future will not have aromatics. Aromatics help SAF match what we'll call the natural oil that's then turned into gas, gasoline or diesel or jet fuel. And so we want Overture to be able to burn both of those. So as we look at the system of the engine and the fuel systems and the gaskets that go into those systems and the other propellers or propellants that go into the moving the fuel around, we want those to be able to operate in both of the aromatics and non-aromatics. That will help. So as SAF increases in its production and usage, that will also help Overture. One of our first American partners, United Airlines, their CEO, Scott Kirby, is very much a proponent and advocate for getting more and more SAF so that even the subsonic aircrafts can burn that SAF. And so he's helping that. I can tell you that from my personal experience flying in and out of Frankfurt, Germany, they have a whole fuel farm that is just sustainable aviation fuel. So it's coming. It's just getting the producers and the distribution aligned with the need of the airlines.
As well as engine design, right, Michael? Yes, the engine design is critical. I mean, for today's SAF, today's engines can burn it. Today's SAF that includes the aromatics, like Troy alluded to, is designed to be more or less drop-in replacement for today's Jet A fuel, which is the most common here in the United States. But there are some subtle details in the engine that would enable that future SAF, like he alluded to. That said, I think there's more to environmental than just emissions. Emissions are incredibly important, but takeoff and landing noise, very important. With Concorde, for example, one of the limitations of Concorde was how loud it was on takeoff and landing in the airport environment. It was dramatically louder than other contemporary airplanes that were flying out of JFK or Charles de Gaulle in Paris, and that would not be acceptable today. The amount of difference between Concorde's operation and other airplanes. So tackling that terminal noise rather than just the sonic boom noise is very important. And then there's other really important factors too, like high altitude emissions. One way we address that is by limiting the Mach number. Troy alluded to the fact that they came down in their design Mach number down to 1.7. I think that's a really important factor to make supersonic airplanes environmentally compatible for the future. It turns out that as you fly faster, you need to fly higher. And there are some complications that relate to high altitude emissions, especially when you get much above 60,000 feet. And so there's a lot of aspects involved in designing environmentally compatible supersonic airplanes. And that's one of the things I love about it. Engineers crave a hard problem to solve, especially when there's kind of multiple technical things that you have to try to juggle all at one time to make the problem work. And that's why it's a really rewarding problem to be involved in and something that you never get bored with.
Thank you. So we only have a few minutes left, so I want to hit two more questions. First, let's see. What advice would you give to students aspiring to pursue research and gain entry into aerospace institutions? This is one of our top questions that people want to know. And with our experience, I think we could provide some insight on that. So Jim, we'll start with you. Go ahead, Clue.
Well, first, I guess I would say if you're interested, go for it. This is a great time to be involved in aerospace. There's a lot of exciting things going on with supersonic aircraft. As Mike was talking about, making aircraft quieter and more efficient, even if they're not going supersonic. And then there's the whole aerospace side of it. We're not here to talk hypersonics, but that's a whole nother level. So yeah, if anybody's interested in getting into the field, obviously study math and science, get off to engineering school and get your degree and get out here and help us.
Mm-hmm. Anything to add, Michael?
Yeah, I knew I originally wanted to be an Air Force pilot, but kind of similar to Troy, I had a injury when I was a kid that disqualified me from that. So I figured engineering was the next best thing. I didn't really have any good role models or prior engineering people to look up to in my family. My father was a butcher and my mom stayed at home. So I basically just did my own research. And like Clue said, the key things are just having a passion for aviation, and that if you are interested in something, it helps you keep plugging along even when the going gets tough. And applying to multiple schools. Don't put all your eggs in one basket if you're a high school senior or a junior. I did not get into my number one college that I wanted to go to. And so make sure you diversify in that so that you have options to continue on. And then once you're in school, just do the work and think about, be intentional about where you want to go with your career. For me, I wanted to design airplanes. And so I kept looking for opportunities to get engaged with that. And thankfully, I found a good place. So over to you, Troy.
Michael, you said it all. I agree with you 100%. It's do the math and sciences. And if you love that, look for that opportunity in college. It doesn't matter what engineering degree you have. I have an electrical engineering degree, and I'm leading the development of an aircraft. So you just have to determine that's what you want to do and pursue it. Don't let anybody tell you you can't do it. You can do it. Back to you, Michelle.
Thank you, guys. So I think what's the most forward-looking or thing that you're looking forward to most when these vehicles become available? Lightning round because we're right at time. Clue.
I'm sorry, say that again, please.
what are you most looking forward to when Supersonics
Oh.
become available?
Well, for the X-59, I'm looking forward to getting airborne and making that first sonic thump. I don't know who's going to get to do that, but the pilots are all going to be vying for that and just prove that this works. And then down the road, when I'm retired and just traveling around the country, I sure be nice to travel on a supersonic airliner that gets me there in half the time.
I can't say it better than what Clue said. Completely agree.
Perfect. I think connecting the world's the main mission here, right?
Yeah.
And that's right at time for us, so I don't want to go over, but thank you guys so much. This was a wonderful panel and super fun to talk to you about. And thank you, NASA, for coordinating all of this and for our audience for joining us today. So enjoy the rest of the event, and over to you, Steve.